I'm going to be talking about three algorithms today and possibly spilling over into the next lecture. Simplex, which was developed in the 1940s originally and was the dominant algorithm for decades, incredibly powerful, used everywhere, and great in practice, but with some real theoretical limitations. I'll talk a bit about the ellipsoid algorithm, which emerged in the 1970s and was and still is just absolutely amazing from a theoretical perspective, but not particularly practical. And finally, I'll touch very briefly on interior point methods, which first emerged in the 1980s and combined some of the practical power of Simplex with some of the theoretical power of ellipsoid. It took a while, but they're becoming quite common and quite popular in practice as well, although Simplex remains the initial choice for just about everything. So let's talk first about Simplex. Remember that we already have an LP algorithm, right? Does anybody remember what our algorithm is for?
Look at all the vertices.
Yeah, just try every basic feasible solution, right? And this works. You can get to the answer, but it's exponential time. More precisely, m choose n, where m is the number of constraints and n is the dimension of the linear programming problem. Okay. So Simplex tries to be a little bit smarter about trying BFSs.
Is this in standard form?
Well, this is true basically for any linear program that you can do this brute force search. But
I mean, if it's in standard form, shouldn't it be choose m of n instead?
Oh, I see what you're saying. No, so yeah, this is more like when I'm thinking about canonical form, right? And I mean, if m is very close to n, then you can be smarter. And like there are lots of caveats to this, but at a high level, you basically, the number of constraints that you need to look at is basically proportional, is basically proportional to the dimension of the problem. Okay. Now with Simplex, we are going to focus on standard form. I mean, Simplex can be described in around any linear program, around any polytope, but the math is easiest to write out when you're looking at standard form. Okay. And we are going to assume, without loss of generality, that A has full row rank. And we've actually already made this argument thinking about solving linear systems and so forth, but let me just sort of sketch it out again. What we'll do is we'll find a basis in the rows, A1 through AK of the rows. Note this might not be the same as the dimension of the problem because we have all of the x greater than or equal to 0 constraints as well. And by definition, any other A sub j is a linear combination of them. Right? So that had better mean that AJ times x, or sorry, that will mean that AJ times x is equal to the sum from I equal 1 to k of AI times x. and that's going to be equal to the sum of those BIs. And so we basically have to have that BJ is, sorry, I forgot my coefficients. So we need some lambda i's here. So it had better be the case that BJ is the sum of lambda I BI. If it's not, then there's no solution. If it is, then it's redundant. Right? So we can throw away all of the other constraints. Doesn't change anything. So now let's think about our basic feasible solution. Okay. What can we say about a basic feasible solution in standard form? Well, we know that all of the AX equals B constraints are satisfied. And so they're sort of automatically tight, right? So what else do we need in order to have a basic feasible solution?
At least the number of dimensions or enough like constraints are tight.
And how many constraints need to be tight in total if we're working in n dimensions?
And
so if we have already these m tight constraints from AX equals B, we need n minus m of the xi greater than or equal to 0 constraints tight. In other words, these have to satisfy xi equal to 0, right? They also, these tight xi greater than or equal to 0 constraints have to form a basis with the AI constraints, right? Because one of the requirements of the basic feasible solution is that we have n linearly independent constraints. Okay. I'll remind you, we're assuming n is the dimensionality of our space. Okay. So let me write this down in picture form. Okay. So the constraints of my matrix involve my A matrix at the top, multiplying by x, right? And this has to equal to, the A constraints times x have to equal to B. But we also have a bunch of these xi greater than or equal to 0 constraints. And we have one for each dimension. So basically I have an identity matrix holding the xi greater than or equal to 0 constraints, right? But I'm going to consider this identity matrix in two pieces. Wow. Sorry, I have to figure out how to reduce the sensitivity of the pencil, but I haven't yet. I've just said that some of these constraints are tight and some of them are loose, right? So in particular, I've got these m constraints of A. And I have another n minus m tight constraints of this identity matrix. So we also have an equality sign over here, right? And then finally, I have, since there's m constraints in total, I have m more of these xi greater than or equal to 0 constraints, but these are not necessarily tight. They just satisfy the greater than or equal to 0 requirement. Everybody happy so far? So these n minus m constraints, let me also draw here a separation. So over here, we basically have an identity matrix of n minus m entries, right? Over here, we have zeros. Yes? Everybody following my picture?
Yes.
Okay. And you'll notice that here, again, there are m of these xi's that are in the not necessarily tight category, right? And m corresponding columns of the A matrix. All right. Now, our BFS is the top n rows. And what I said is that they're a basis. In other words, they are linearly independent rows. Right? So this square matrix at the top is non-singular. Okay. So that means equivalently that the matrix made of the top n rows here has linearly independent columns. Right? So looking at the funny shape of this matrix, how can I think about what makes the columns linearly independent? Or let's ask the converse. If there is some linear combination of the columns that sums to 0, right, violating linear independence, where could those columns come from? Right, I can just visually inspect this and see that some of the columns could not possibly appear in such a linear combination.
They must have only come from the last m columns.
Exactly. Notice that the first n minus m columns can never cancel. Right, because each of those columns has an entry of the identity matrix where every other row has a 0. Sorry, every other column has a 0. So if you ever took that column, you would stay, that coefficient would stay non-zero. Okay. So I don't have to worry about those, right? Those are certainly linearly independent columns. I only have to worry about the last m linearly, the last m columns. Okay. So there's only a problem.
Excuse me, you want to prove that the columns are independent?
No, I'm working from the definition of a basic feasible solution, which states that the rows are independent of the basic the row constraints of the basic feasible solution are independent, which means that this n by n matrix on the top is non-singular, right, which means that its columns are independent as well.
Right.
Okay.
But then,
so now I'm just sort of exploring what that means, right? This is all still just working with definitions. I'm not proving anything yet. So if there is going to be a failure of linear independence, which we know there isn't, it only fails if the last m columns are not linearly independent, right? So the thing to focus on, if we want to understand that this really, if we want to verify this really is a basic feasible solution, is these last m columns. And of course, the bottom n minus m rows of these columns are 0. So really all that matters is the last m columns of the A constraints. Actually matter. Okay. So this, with this sort of investigation, I can now give you another definition of the basic feasible solution, which is that, or of a vertex of the polytope, because those are the same thing. We have to satisfy AX equals B. And we also have to have that there are M linearly independent columns of the A constraints that correspond or that include, notice that, remember that a column goes with each variable, with each xi, right? So these linearly independent, these last M columns cover all the slack xj's, right? Remember that we said that these xj's, or these xi's in the top of at the top, the ones that are in the upper matrix, they're all tight at x equals 0. So the only ones that are slack are the bottom M x's, which correspond to the final x columns of the A constraint. And if these columns of the A constraint are linearly independent, then the entire upper matrix is linearly independent, because by definition, no combination of the last M columns sums to 0. And we know that we can't, if we try to include the other columns, they can't sum to 0 either. Okay? So this is what I wanted to arrive at, this alternative definition of a basic feasible solution. Does everybody understand that this is the same thing?
I didn't get the last part, sorry.
Sure. So let's break it. So let me go the other direction. Suppose that we have a suppose that we have an X that satisfies these two characteristics, that AX equals B and that M linearly independent columns all satisfy, cover all of the slack xj's, which are not 0. Okay? Why is that a basis? It's a basis because we start with these M linearly independent columns, and we then, right, so those can't sum to 0, regardless of what coefficients we combine them with. We then look at the other columns of the matrix, of the upper matrix, which includes the top part of the identity matrix. And so those columns also cannot sum to 0 with any coefficients, because those entries from the identity matrix will never get canceled out. Okay, so that shows me that all n columns of the upper matrix, right, the first n rows, all of those columns are linearly independent, so they form a basis. That tells me that this upper matrix, this n by n matrix at the top, is non-singular, which means that its rows are also linearly independent. And that tells me that those n rows are n linearly independent constraints which are tight for the given x. And that's the definition of a basic feasible solution, is it's a point which has n linearly independent constraints tight.
So at one point, like you're saying that the M columns of A are linearly independent, and so is the n minus m other columns, because they include the identity submap.
Correct.
But I mean, why there is not a combination of all of them which becomes 0?
Because even if I combine all of them, I'm still carrying that identity matrix along. And so I can't, right? I have some non-zero values from the first n minus m columns. And whatever I do to bring in the last m columns, I'm still going to have those non-zero values. Because the last m columns have zeros at those coordinates.
Right, got it, thanks.
Okay, good. So
I ask another question, Professor?
Absolutely.
What do you mean by the constraints cover all slack xj? Like, what's
in other words, so there's a correspondence, right, between columns and variables, right? Each column is associated with one variable, one of the xj's. Column j goes with xj. And so what I'm saying is that all of the, I mean, given the way that I've arranged the columns, all of the slack xj's, all of the xj's that are not 0, have to be in the last m coordinates of the x vector. They have to correspond to the last m columns.
I see, thanks.
Right, because the way that I drew this matrix, right, I said that the upper n minus m entries of the identity matrix are tight constraints. So only the lower m entries of the identity matrix can correspond to slack, tight constraints xi equals to 0, which means that only the bottom m constraints can be slack constraints where xj is greater than 0. Okay? Good. So now we have this alternative definition of a basic feasible solution. And now I can add in some other definitions. The set of the last m columns is called a basis. And it is a basis of its m coordinates, but we're using the term more specifically now for the simplex algorithm. The corresponding xj variables are called the basic variables. And the other variables are called the non-basic variables. And so I'm going to use B to denote the set of basic variables and N to denote the set of non-basic variables. Now, I would like to point out that if you're just given the basic set, you can actually compute the coordinates of the vertex x. Okay. So how do we do that? Well, let me write AB for the B columns of the matrix A. All right. Notice that A sub B is an m by m matrix and full rank, because all of its columns are linearly independent. Okay. So that means it's invertible, and I can solve the linear system that says that AB times the XB variables. Remember that XB is M variables, so the dimensions match up. I'm going to make that equal to B. And I'm also going to set the other variables xn equal to 0 because they're non-basic, they're tight. I know those constraints are tight at the basis. Okay. And so that gives me the value of all of the x coordinates, right? So again, looking at the picture, right? I know that the upper non-basic variables are all 0 at this basic feasible solution. And so I can set those to 0. And now the constraints that AX equals B, well, I've got this bunch of 0 variables. I can ignore those columns. So all that's left is a requirement. It is the final m columns, which create A sub B. And those have to multiply by the final m variables, x sub B, to produce the values B. Make sense? Now, I also notice that you can have many different bases, multiple bases, B, for the same vertex X. Why is that?
we can have more than n minus m tight constraints at 0.
Exactly.
At least that much.
Exactly. I mean, it's quite possible that in this linear program, you know, the all zero vectors is feasible, right? So then all of the constraints are tight. And so there's really no restriction on my choice of basis columns to satisfy the requirement that I cover all the slack variables. Okay. So if only a few variables are slack, then there may be many, many bases corresponding to that vertex. If I have m slack variables, then that defines the unique set of columns that has to specify that can be basic for that vertex. Okay. Whoops.
Wait, just to make sure, so this is due to constraint redundancy, right?
It's not due to constraint redundancy. Sorry, let me think about that.
As in like the slack constraint, like the greater than or equal constraint is like is linearly dependent to the constraints, the equality constraints from AX equals B.
I think that that's correct. I have to think about it. No, actually, I don't think that's necessarily true. I could be kind of silly and put a constraint like x3 equals 0 into the A matrix, right? And so then the x3 greater than or equal to 0 constraint would not be linearly independent of the A matrix. Okay. So I have to be a little careful there. So again, continuing on with alternative definitions, I can now summarize this by saying that X is a vertex if there exists a basis B such that the non-basic variables are all 0. This submatrix, which is m by m, is non-singular. And the solution for the basic variables, namely AB inverse times B, which is equal to XB, is greater than or equal to 0, because this is required for feasibility. Okay? So this is just notation juggling. We're still talking about the same notion of a basic feasible solution. But now that we have it, we can talk about what the simplex does. So Simplex tries to be clever about searching through the basic feasible solutions by using what's basically local search. You start at some BFS, and then you move to a better one. Until you can't. Okay. So, at the risk of dismaying all of you with my disastrous drawing skills, here is a polytope. And perhaps we start over here and are trying to optimize in a direction like this one. What would be a natural sort of local search, right? A way to modify this solution looking for a better one, right? So this solution is an intersection here of three tight constraints, three sides of this cube, right? Where could I relatively easily compute other vertices that I might consider for improvement?
You can try to swap one tight constraint for another one, which is like following along one of the edges.
Exactly. So the idea is to follow an edge. To a new vertex. Okay. And hopefully the edge is, you know, positively aligned with the objective function so that it improves the objective value. Okay. Now notice that an edge is defined by n-1 type constraints. Okay. So what I'm basically doing is swapping out one of the n and replace it with the next one I hit. On the line. So does that geometric picture make sense? So now let's fill in the math. Okay. So we had this linear program that said AX equals B, but I'm at a basis. So I'm going to rewrite it by breaking apart the A matrix into its non-basic, and its basic components, which is columns, which are going to multiply the non-basic and basic variables to yield B, right? Or writing it out, what I'm basically saying is that AN times XN plus AB times XB is equal to B, right? But notice that this is true for any X, not just for my current vertex, or any feasible X. Not just the vertex. Okay, so the vertex is the point where xn equals 0. But I can use this formula anywhere. Okay, and in particular, I can also write, I can rewrite this by saying that that xb is equal to a sub b inverse, and this is why it's important for a sub b to be non-singular, times b minus a sub n times x sub n. Yes? So again, I'm thinking about moving from my vertex. I'm going to move by modifying some of the xn's, and this is going to tell me how I should change the xb's I'm going to actually move by, so this tells me the relationship between xb and xn as I modify. Now I can also write the objective, cx, by breaking apart the basic and non-basic parts. So that's cbxb plus cnxn. But now I can plug in my derivation of x sub b. So, So that's going to be AB inverse times B minus A sub n xn. And then I have to add in Cn times xn. Okay. And now I will rewrite this to gather up the xn terms. It's CB times AB inverse times B plus Cn minus CB AB inverse AN times x of n. Okay? Now you'll notice that this is a constant, and this depends only on xn and doesn't mention the basis variables xb at all. Okay? So since the first term is a constant, this improves or worsens just based on the second term. Okay. So that leads me to define a collection of reduced costs. It's a phrase I'm sure you've heard before, which I will write as Cn twiddle. And I'm going to define them as the coefficients in the second term, Cn minus Cb times AB inverse times A sub n. Okay. And now I can observe that Cx is equal to some constant plus the reduced costs dot the non-basic variables. Everybody with me?
I had a question about it being constant. I guess the basic variables can change though, right?
Yes, sorry, so I should have been clear. What I'm doing now is taking the perspective of a particular basis, the particular vertex that I'm at right now. And now I'm going to analyze my objective function from the perspective of that basis. So I've rewritten my objective function so it only depends on the non-basic variables of that basis. And now I'm going to imagine moving away from that basis. But as I move, I'm only going to have to track the non-basic variables, because I figured out how the basic variables will update in response. Okay?
Yeah. Okay.
Still wondering? But yes, so basically I'm holding the basis constant. I'm not changing which variables I call the basic variables. And as long as I do that, the first term and the coefficients are constant, because all they depend on are which are the basic variables.
I guess my issue is just that, like, when you're flipping out one equality constraint for another, like that is flipping one basic variable for another.
That is correct, and that's what we're going to do at the end of our movement.
Okay. Okay.
Right? While we're moving, we're stuck with this. We're working with the basis we have now.
Okay. Gotcha.
Okay. All right. So I've got this expression that I've got this expression for the objective function as a constant plus some function of the non-basic variables. Okay. And so that's a change of perspective, but it's a useful change of perspective. Can you give me a condition that will tell me that I'm actually at the optimum vertex?
So if we're like minimizing,
Yep.
like the C tilde n would be, I don't know if I'm saying the name right, but it would be if it's all positive.
Exactly. So notice that if C tilde n is greater than 0, or greater than or equal to 0, then all feasible points, actually, let me invert that. No feasible points have a smaller objective. Can somebody explain why?
Because at the vertex, all the xn have to be 0, and if we move away from it, then the xn must be increasing.
Exactly, right? Our vertex have all xn equals 0. Any feasible point has all xn greater than or equal to 0. So it's only going to contribute a positive value to our constant that we've already achieved. And so it's going to be, or a non-negative value. So it's not going to be any better. Okay. We are optimum. We're at the optimum if all the reduced costs are positive, are non-negative. Just like min cost flow. Right? So now suppose some non-basic Cj is less than 0. That's going to happen if we're not at optimum. How do I improve my solution?
You
Go ahead.
you can follow you can swap out the basic feasible with like xj in it.
Right. But I'm going to talk about it in continuous terms. How would I achieve a sort of an infinite, how would I, continuously improve my solution from where it is now? Well, I would increase xj, right? As xj gets bigger, my objective value decreases because Cj is less than 0, right? Okay, I'm increasing xj until what happens? Well, sorry, actually, before I get to the until, note that this modifies x of n.
And
that means that it modifies x sub b. Right, because we wrote x sub b to be a function of x sub n, right? As AB inverse times b minus an xn. Yes?
Wait, what's that term we're decreasing? The I couldn't really read it exactly. To decrease it, increase xj to decrease. What is that?
Oh, to decrease the objective function.
Okay.
Okay.
Are we using?
So we found this xj with a negative reduced cost. We start to increase that xj from 0. As we do this, there is a corresponding change in the basic variables x sub b. And we do this until when? When do we have to stop?
Until one of the HB variables is now tight, becoming 0.
Right. So we keep going until we hit xi equals 0 for some basic xi in the xb set. Yes? Because at that point, if we keep going, we'll get to xi less than 0 and will become infeasible. Okay? So notice what we did. Xj was 0 because it was non-basic. We start increasing it, so it becomes slack, right? And we keep increasing it until xi becomes 0. In other words, it becomes tight. Okay? So what has happened is that xj is now slack, and it enters the basis, replacing xi, which is now tight. Okay. So again, this is the math of loosening one constraint, moving while you keep the other constraints tight until you hit a different constraint. So this is the math of moving along one of the lines of the polytope. Make sense?
I have a question.
Yes.
So it makes sense to me, like when we're at the start, when all xn are 0 and like xp is what it is, it makes sense to me, like if we move by an infinitesimal amount in like whatever xj we choose, I can accept that we're minimizing cx, but as we're going forward, we might change a, b, and we might...
Absolutely. You're absolutely right. So the point is that since xj enters the basis and replaces xi, this creates a new b at our new vertex. And we have to start the whole analysis over with this new b, right? We now start analyzing from the perspective of the new basis.
No, like, I mean, like, I can accept that at the start, increasing xj would decrease the objective, but what about halfway?
Well, again, remember that the definition, right? So wherever we are, there's a basis. And whatever that basis is, we can identify these reduced costs for the non-basic variables of our current basis. And we can write the value of the objective function in terms of these reduced costs. And therefore, if any of the reduced costs is negative, as defined by our current basis, the one we reached in the middle, if any of those reduced costs is negative, then increasing that non-basic variable decreases our objective function further.
I see. Thanks.
Sure. These are great questions today. Keep them coming. Okay. So this is called a pivot. When we swap out one basic variable for another. And the simplex algorithm is just pivot until you find the optimum. Okay. And if we want to fill in a little bit of the details, right? We're doing some linear, to do a pivot, we have to do some linear algebra over an m by m matrix to sort of get our reduced costs and such. And then we need to test n constraints to see which gets tight first. Right, so the runtime of a single pivot step is going to be, you know, to test the n constraints, we're going to have like n squared time, or so. Sorry, is that right? No, actually, we're going to be solving a bunch of n by m problems. I think what basically happens is that you solve n problems on an m by m matrix. So the key point is that this is certainly polynomial in m and n, which is what we need. Okay, But sadly, some things can go wrong with this approach of pivot, pivot, pivot until you're done. Or there's some details that I didn't fill in. Anybody wondering about some details?
How many times do we need to pivot?
Okay, so there's the number of pivots. I'll come back to that one. Let me ask about other details.
It's kind of similar to number of pivots, but like kind of infinite pivoting. Like you could loop, it seems.
Right. So actually, that's a very good question. Can we have loops in pivots? How would a pivot loop arise?
I mean, it wouldn't, because every time we're doing this, we're improving. So, you know.
Actually, let's be careful about that. So let's think about this pivot, right? I found this non-basic variable, and my idea is that I can increase it until some other basic variable becomes tight, right? But what I would like to point out is that I misspoke a little bit. Because the problem, no, actually that's okay. So I had this basic xi, right? And I'm going to stop when xi reaches 0, right? That's when I have to stop increasing xj. So what can go wrong with that?
Well, I mean,
We don't be able to move from the current ones.
Sorry?
We might not be able to move at all.
How come? What would stop us from moving?
Sorry?
What would stop us from moving?
If one of the basic, one of the variables in the basics is already 0.
Exactly. If this xi that I'm talking about here is already 0, then I can't increase xn because it would immediately make xi infeasible, right? So maybe increasing xj hits a basic xi that is already 0. Now, from an algorithmic description point, this is okay, because we can that would still allow us to add xj to the basis and remove xi, right? But xj is also 0, so we haven't made any progress. We haven't changed the objective. And so now maybe, you know, our next pivot has the same problem. It can again swap something into the basis without changing the objective function. Basically, we can perform this whole series of swaps that never change the objective function. Okay. So we can create a cycle of pivots that never ends, that never improves things. Okay. And to avoid this, you have to design a guaranteed non-cycling pivot rule. And a really important question is whether there is one. Okay. And that actually took quite a long time to figure out. The answer is yes. And as an example, there is the rule where what we would call the lexicographically first pivot rule, which basically says that you always increase the first xn that is increasable. And when you have an option of multiple basis vectors to bring into the basis, I think you put in the last one. So essentially, when you have more than one possible vertex to go to, or more than one possible basis, you always hunt for the lexicographically first basis. And you can show that that will never revisit, because you're guaranteed that you're always improving the lexicographic order of your basis. Okay, so these do exist, and you can prove that they work. There's another problem.
I mean, why even there is at least one option that you can increase?
Well, remember, there has to be an option, because the only way that you're not at optimum is if there is a negative reduced cost.
But there might be negative reduced costs which are not increasable.
That is correct. But the point of the lexicographic pivoting rule is that even if there's no improvement in the objective, as long as you pivot according to the lexicographically first rule, you'll never get the same basis more than once. Okay? So if you never visit the same basis more than once.
Okay, so there's something non-trivial, I guess, that.
Absolutely. No, this is non-trivial to argue that there is an acyclic pivoting rule. Okay. But if you never visit the same basis more than once, what does that tell us about the runtime of this algorithm, or the completion of this algorithm?
That's finite.
Right? Exactly. There's a finite number of bases. And in particular, that tells you that you're only going to have m choose n pivots. And so there's a finite runtime.
So this claim is that during the whole algorithm, we don't visit one basis twice, or is it just during the time that we cannot increase?
What you can prove is that during the entire algorithm, well, remember, so this strategy will never make the objective function worse. So if you ever make it better, you're guaranteeing that you'll never revisit those bases again, because their objective function is worse than what you have now.
I see. That's
okay. So yeah, basically, if you're looking at this simplex algorithm, what's going to happen is, you're going to move to a vertex, and there may be many bases that correspond to this vertex, or there may be many vertices that all have the same objective value, and you're going to spend some time pivoting around, moving without changing your objective value, but eventually you'll escape. You'll find some basis that leads to a better objective value. And then the whole process may start again, but you'll never visit a vertex more than once, and so you have this bound on the runtime. Okay? Now there's one more issue that I haven't addressed, right? My algorithm said, start at a vertex, go to a better vertex, and then go to the next one, then go to the next one, and so on and so forth, right? What is incomplete in that algorithmic description if you wanted to implement that?
We need to start at a vertex.
Good. We need a starting vertex. Okay. Now, if you think about it, what that means is that we need a feasible point. Right? I mean, a vertex certainly is a feasible point, and I already showed you that if you have a feasible point, you can round it to a vertex, right? But wait a minute. Finding a feasible point is just as hard as optimizing, right? That's one of the things I showed you in LP duality. Right? So if it's just as hard to find a feasible point as it is to optimize, then why is it helpful, or how have I made things any better if I've given you an algorithm that needs to start with a feasible point? Well, this is true in general, but not for specific polytopes. So in particular, what I'm going to do is I'm going to take my initial polytope, and I'm going to express the problem of finding a feasible point as as the value of a different, as the problem of optimizing a different linear program. Okay. So we're going to find our feasible point by optimizing a different LP. And that LP, let's call that, I've already used B, let's call that LPQ. And the point is that in Q, it's easy to find a feasible point. And then the optimum of Q gives a feasible point for our LP. And you will do this on your homework tonight, okay? So that takes care of all of the sort of loose pieces of the simplex algorithm, and now we have a complete implementation. Are we happy? Well, not entirely, because all we know is that the runtime is finite, right? It's bounded by m choose n. And actually what that tells us, you know, we already had an algorithm with an m choose n running time of just trying all of the points, all the bases. So what did we accomplish? And it's not clear that we accomplished anything, right? So this simplex algorithm is not apparently polynomial. Right? And so algorithmicists have been working now for 60 years to try and figure out whether there is whether the simplex algorithm is polynomial, or whether there is a polynomial simplex algorithm, right? Notice that simplex algorithm is kind of a meta algorithm. You invent whatever pivoting rule you like, and that gives you a simplex implementation. So maybe some pivoting rules are bad and some are good. And we've learned a lot. So people define, Klee and Minty defined the Klee-Minty cube, which is basically a hypercube, which is slightly twisted so that all of the vertices are out of line. So they all have different objective functions. Their objective values differ. Okay. And they showed that many pivoting rules visit all the vertices of this cube. So they all have lower bound exponential running times. Okay. But that's only many pivot rules. It's not all of them. There might be a polynomial pivot rule. Okay. And trying to creep up on that, we had a mathematician introduced what's called the Hirsch conjecture. I'm sure you can guess what his name is, which is about the length of the path in a polytope. Or actually, I should just say the max diameter of a polytope. In simplex steps. So, you know, if we jump back up to this cube that I drew long ago, you see that I can move from any corner to any other corner by taking 3 steps, right? Three pivots will get me from one corner to another corner. Okay. So Hirsch conjectured that if you have a polytope of m constraints over n dimensions, that the maximum number of pivot steps that you would need is only m plus n. Okay, linear in the number of constraints and dimensions, right? Now, that doesn't prove that there's a good simplex algorithm because this path might not be monotonic in the objective function, okay? But it will at least give some hope that there's a good simplex algorithm, a good pivot rule. Unfortunately, this was disproved. Santosh proved that the diameter is at least 1 plus epsilon times m plus n. In when did they do it? In 2010. So this is pretty recent work. Okay. So the Hirsch conjecture is false, but in a way that doesn't matter for what we care about, right? If you could achieve 1 plus epsilon m plus n, you would still have hopes of a linear time simplex algorithm. Okay. Kalai and Kleitman showed that the path length is at most m to the log n. Okay. Which is way better than m choose n, right? This is basically m choose log n, right? So tremendous improvement and almost polynomial if you think of log n as a small number, okay? And they also gave a simplex algorithm with a running time of like 2 to the square root of n, which again is significantly better than the m choose n algorithm. Okay. We also had Spielman and Tang who performed what was called a smoothed analysis. They showed that any simplex, any LP problem with small random perturbations in the constraints has a fast simplex algorithm. So there might be some really pathological LP problems where simplex is slow, but if you just jitter it a little bit, you get one where simplex is fast.
Excuse me, what is the pivoting rule for this?
I don't remember. I think pretty much any pivoting rule works in that case. Okay, because these small random perturbations also ensure that no two vertices have the same objective value, and also ensure that there's no what's the word? There's no redundancy in constraints. All of the constraints are now going to be linearly independent of each other. So you actually can't get cycling pivots. Okay.
But you mean cyclic pivots or a result of the constraints to be dependent?
Yes, because I mean, if you think about it, when I do a pivot, right, I change the set of constraints that are defining my basic feasible solution. But the cyclic pivot arises when the new set of constraints yields the same vertex as the old set of constraints, which means that you have more than n constraints that intersect the same vertex.
You mean the set of columns?
Yes.
Okay, I said the rods of the matrix.
Okay. All right, other questions?
Is the Kalai here, the Yo Kalai from our department?
Yep. Oh, sorry, no, sorry. It's Danny Kleitman from our department. Gil Kalai was at our department, but I think he's in Israel now. Maybe I'm wrong.
Cool, thanks.
Also, there's a Kalai who's his dad. There's Gil Kalai and another Kalai, and I've suddenly forgotten which one did this. But I think it was the younger. Okay? But Spielman was also at MIT. So, you know, once again, MIT rocks. We have all the coolest results in algorithms. But he went to Yale, so we don't like him anymore. All right, any other questions about Simplex? I've actually got some more things to show you about Simplex, actually. But any questions about the algorithm? So let me show you one little addendum regarding Simplex and duality. Okay, remember we had these reduced costs where we said Cn tilde equals Cn minus Cb AB inverse An. And when all the Cn tilde are greater than or equal to 0, we have an optimum, right? So let's look at that optimum. Let me define a vector y as Cb times AB inverse. Okay. So that, of course, Cb is equal to YAB. Okay. Now, notice that y times An is equal to Cb AB inverse times An, right? But that shows up in my reduced costs, right? So in particular, I know that y, let me see, so I just want to get my dimensions right. So here, Cb AB inverse times An, that's equal to Cn minus Cn tilde, right? But I've just said that all of the reduced costs are greater than or equal to 0. So that tells me that Yan is less than or equal to Cn. Right? I also know that YAB is equal to CB. So if I put those together, that tells me that Y times the combination AN and AB, right? We have equality and an inequality, so I can combine them together and say that they are, that it's less than the corresponding coefficient. In other words, YA is less than or equal to C. Yes? Also, by definition, right, I wrote YB, that's equal to C, Y times B is equal to CB times AB inverse times B. But we said that AB inverse times B, that's the definition of XB. And that is equal to CX, since Cn xn is equal to 0, since xn is equal to 0. Okay? So in other words, this y that I defined satisfies ya is less than or equal to c, and yb is equal to cx. What does that mean?
Optimal for dual.
Y is a dual optimum. Okay. And you'll notice all I needed to compute Y was the basis. right? I just needed the basis. So simplex, right, which is finding the basis for the optimum x, also finds the optimum y at the same time. Okay, they both are revealed by finding the correct basis. Okay, more generally, any basis gives some y. It just might not have the right objective value. But we can look at yb minus cx as that gives the duality gap and says how far we are from optimum. Right, so at any time running the simplex algorithm, we have a current primal solution. We can also read off a current dual solution, and we can compare their objective values and know that the optimum is somewhere in between, and that tells us how far away we are from the optimum. Okay.
Excuse me, can I ask a question?
Yep.
Why is the y vector feasible for the dual necessarily?
Because y is less than or equal to c. That's the definition
for
of
any arbitrary basis.
Sorry, it's for sorry, not for any arbitrary basis, but when we have actually, let me back up from what I was saying. You're right. Sorry, maybe I was claiming too much here. Let's not talk from duality gap. Does simplex give me a dual? No, I think you're right. I think I overclaimed. I'll check that and answer back next class. But let me point out that this gives another way to prove strong duality. Which is to prove that simplex terminates. E.g. by giving a non-cyclic pivoting rule. Because when simplex terminates, we have these non-negative reduced costs, and that gives us an optimum dual and shows us that their objective values are equal. Okay, so we used a kind of a structural physics-based argument to prove strong duality, but this gives you a way to prove strong duality algorithmically. Okay, questions? There's one really big question remaining.
Do we have a strongly polynomial algorithm?
Actually, not even that. Is there even a weakly polynomial algorithm? Is linear programming polynomial? Right? So in practice, I should say, simplex is often fantastic. However, as we saw before, right, we only can prove exponential bounds, and we don't know if we don't know if there's a lower bound. We're not sure if there's any simplex algorithm that works in polynomial time. So on Friday, I'll start to answer this question. I will talk to you about the ellipsoid algorithm, which is actually a weakly polynomial time algorithm for linear programming. All right, and so this was a tremendous theoretical breakthrough, which was achieved in the 70s, to show that there is a polynomial time algorithm. but it's not a good algorithm for practice. Interior point, which was developed in the 80s, is polynomial time, and thanks to a lot of work, is practical and in some cases beats Simplex now for certain kinds of problems. So on Friday, I'll give you a relatively complete but high-level picture of ellipsoid, and I'll give you a really hand-wavy sketch of how interior point works. And then we'll be done with combinatorial optimism, with this sort of chain of polynomial time algorithms, and we'll begin to spend a couple of weeks on what to do about problems that are not polynomial time solvable. So we'll be looking at NP-hard problems and how to approximate their solutions. Any final questions? Okay, look for a problem set later tonight, and I will see you all on Friday.